Welcome to the walkthrough of Assignment 3A for my CS253 class in the fall of 2023. The purpose of the first part of this two-part assignment is to deepen your experience using Java functional programming features and their integration with Java sequential streams. In particular, in this assignment, you'll develop an app that uses Java sequential streams to obtain, transform, and store images. The code you write for this assignment has a GUI and runs as an Android app. Please feel free to use this app to help debug your solution. The following resources may be helpful in completing this assignment. They're good overviews of Java streams here and here, and the book Modern Java in Action is a great resource to learn how to program Java streams. Naturally, we'll cover this material in class, which will be available in my YouTube CS253 playlist. The Image Crawler app is packaged as a project using Android Studio. This app is written in both Kotlin and Java and demonstrates many Android capabilities. For the purposes of Assignment 3, however, you only need to be aware of the following directories. Image Crawler crawlers, which contains the skeletons you need to fill in, as described below, and Image Crawler source test, which is a set of unit tests that exercise the features you're implementing to evaluate whether you've correctly satisfied this assignment's requirements. To compile this code, you need to use the provided Android Studio project. You can run this project by clicking the green Run App button in the Android Studio IDE, which should automatically select an Android emulator to run, assuming you have one created. The app's minimum API is 31, so you need to select an emulator that uses an API greater than or equal to 31. I recommend API level 34. If you don't already have an Android emulator, you can create one by clicking on the AVD Manager button in the Android Studio IDE. You'll need to modify several files containing the skeleton Java code by completing the to-do you fill in here tasks to provide a working solution. Don't change the overall structure of the skeleton. Just fill in the to-do tasks and don't delete the to-do markers, or your code will not be reviewed. In particular, you need to finish implementing the following to-do tasks for this assignment in the Image Crawler folder. First, you need to modify the sequential streams crawler.java file and complete the to-do tasks in various methods to obtain, transform, and store images. This class uses Java sequential streams to perform an image crawl starting from a root URI. Depending on the parameters used to run the tests, images from the HTML pages reachable from the root URI are either downloaded from a remote web server or read from the local file system, and the results are stored in the local file system on the Android device. You'll also need to complete the to-do tags in the student.kt file to set the type field to include just graduate or undergraduate, depending on which version of the assignment that you're implementing. The bulk of the code for the app is provided in the skeletons. In fact, a complete solution using Java 7 features is provided in the sequential loops crawler.java file. You'll therefore convert this Java 7-based class to the sequential streams crawler class that uses Java sequential streams. Your solution should use no loops or if-else statements in the assignment, and instead use Java sequential stream aggregate operations and functional programming features. Your solution will be considered correct if it passes all the unit tests, is commented thoroughly, and addresses my review comments. Skeleton code for this assignment is available here in my GitHub repository. Now that you've set up your GitLab account, you can pull this skeleton code in your repository, read it carefully, and complete the to-do markers. Unit tests in the Image Crawler source test folder are provided to increase our confidence that your implementation is working as expected. It's essential that you use the Android Studio GUI to run these unit tests locally on your computer, as described here and shown later in this video. As usual, testing only demonstrates the presence of bugs, not their absence, so don't rely solely on the test to detect problems in your code. In particular, I'll also provide videos that walk through frequently made mistakes that you should address. Please address these issues prior to your submissions to streamline our programming assignment review and assessment process. Assignment 3A is designed to deepen your experience developing apps using Java sequential streams and functional programming features. The skeletons and unit tests are quite extensive, though you don't need to understand them all to complete your solution. Please therefore start early and ask questions in class, office hours, and on the discussion forums to ensure you complete this assignment successfully. Now that we've walked through the specification for Assignment 3A, let's go ahead and take a look at the skeletons you have to fill in. First of all, make sure that you fill in the fork join crawler skeleton and the fork join EX crawler skeleton using the solutions that you did for Assignment 1 and 2, respectively, making sure that you fix any problems that I noted and also ensuring that all your tests pass. Super important to do that. Do not forget to do this, otherwise you'll lose lots of points unnecessarily. So let's go ahead and take a look at the sequential streams crawler. This is another image crawler implementation that uses the Java sequential streams framework to perform an image crawl starting from a root URI. It behaves very much like the previous implementations, the main difference being this does not use any parallelism at all. So all stream operations are performed in a single thread of control using Java sequential streams. Naturally, the performance of this will not be as efficient and scalable as the previous two solutions, but of course, we're really just setting the stage for the parallel streams implementation that will take place in assignment 3B. So let's come down here and take a look at the skeletons. So the first skeleton you need to fill in is the perform crawl method. And down here, you should make a single element stream that will call the crawl page method and then count the number of images that were processed successfully. That should be pretty straightforward to do. You'll have to think a little bit about how to do that, but there's nothing much confusing or complicated there. The crawl page method is going to require also creating a single element Java sequential stream and then using some stream intermediate operations such as filter and map and so on in order to be able to check to see if the current depth is within the max depth, if the URI hasn't been visited yet, and then you'll call the appropriate helper method to crawl the page. And I think it's pretty clear what you'll call. You'll end up calling process page, and process page will also create a Java sequential stream and use some other helper methods similar to what you've done before in order to get all the image and page elements from the page, which is the parameter. And then it'll call some helper methods to crawl or process these elements and return a stream of image objects. Note that now that we're doing a single-threaded sequential stream, there's no need to do the manage blocker stuff that we were doing before. We will revisit that and bring it back for assignment 3B, but right now we're all in one thread of control, so there's no need to worry about those calls. So that should simplify things a little bit. Down here we have the process image method, which is something that'll be called under the right circumstances by process page. And what this does is you'll end up creating a one-element Java sequential stream that either gets or downloads an image from the given URL, this thing here, depending, of course, whether the image is cached or not. And then you'll use some other helper methods that are defined up in the image crawler superclass and call a helper method in this class to transform each image and return a stream of transformed images. Now, there's only one method left, so it's pretty clear what's going to be called from this, and that will be the transform image method. And here you will use a Java sequential stream to filter and transform and store an image using various helper methods defined in the image crawler superclass, and you return a stream that contains non-null transformed image objects. So a couple things to note here. Again, one, especially up here when we're doing the downloading of the image, we don't need to use the manage blocker stuff. In fact, if you take a look in this file, you'll see we don't have those helper methods here at all because this is just a single threaded implementation using sequential streams. So this code is actually very lean and mean. It should be straightforward to do. You'll need to use various methods that we've talked about from the Java Streams API, things like map and flat map and filter and so on. And you'll need to reuse some of the helper methods that you've used before in the previous assignments. The main difference here is there's really no parallelism going on, so we can strip away a lot of the pieces. And you'll also notice we don't have to have all those nested classes that inherited from recursive task that we had in the fork join EX crawler and the fork join crawler implementations from the previous assignments 1 and 2. So that's really all there is to it. This should not take you very long, and we have unit tests to make sure that you're doing things in a sensible way. So now that we've walked through the specification and the skeletons for assignment 3A, let's go ahead and run the unit test that I provide. There's two ways to do this. One way, you can go up here and run the tests in the little blue box at the top, and you can also come down and run the tests by right-clicking like this. Let's do it that way. They both should give you more or less the same results, hopefully exactly the same results. So you can see that we're compiling the tests and running the tests. A couple of things to note right off the bat. There are 3 sets of tests. One set of tests is for assignment 1, another set of tests is for assignment 2, and the latest set of tests for assignment 3. You absolutely must make sure that all of your tests run. You should get green test marks, check marks for all the tests, not just the one for the latest assignment. People keep unnecessarily losing points. This very important topic, we discuss it in the beginning of the course. It's in the frequently asked questions file. So make sure you run your tests and make sure all your tests pass. If, of course, you have any problems or any questions with tests, make sure you come to office hours, post questions on Piazza, and/or ask questions in class. Now that we've walked through the specification, the skeletons, and the unit tests, let's show how to run the app. So to do this, we'll come over here and select one of the implementations. We'll do sequential streams to start with, and then we simply click on the download button, and you can see that the images are being downloaded, filtered, and stored sequentially, essentially from left to right, top to bottom. You'll see each image is first downloaded, then we apply the various image transforms, which are then stored and displayed here. So you can see that this is all a very sequential process, and there was only one thread of control, and it took roughly 10 seconds to do all this work. Keep in mind this is on the emulator, so these times are not necessarily reflective of what you would see if you were running on an actual mobile device. Now let's come over here and we'll select a different implementation. Why don't we do the fork join implementation? This is what we did for assignment 1. And now let's go ahead and download and run everything. And what you can see is that it's being done in parallel. Look how much speedier it is and how much more mixed up everything is also, because it's doing everything in parallel in different threads. So we don't have this kind of left to right, top to bottom sequential processing phase. You'll also notice it took about half the time to do the processing. Again, your mileage may vary since this is the emulator, but I think you get a feeling for the fact that the parallel processing is considerably faster than sequential processing. And then just for kicks, the final one we'll do is run fork join EX, and let's see if that runs quickly as well. You can see it also does things in different orders, just like the fork join test, and this one ran even faster. So demonstrating once again that parallel processing can make a big difference in the performance of your applications, even when running in an emulated environment, such as the one I'm showing here.